So good afternoon. Today is the week 5 of the live interaction session for the NPTEL course Introduction to Atmospheric and Space Sciences. So last week we were discussing virtual temperature. So this is where we stopped in the last week. So as we discussed, the value of gas constant, which is Rm, for moisture will depend on how much water vapor exists in the air. So if you remember, we were discussing about the specific gas constant for dry air, which is Rd, and we also know what is the value of specific gas constant for water vapor, which is Rv, which is around 461, and this is around 287. Suppose we have a moist air parcel which has both dry air plus water vapor. So if only dry air is there, we will basically use the value of Rd, which is 287, and only if we are considering water vapor, then we use the value 461. Suppose we are considering a moist air which has both dry air and water vapor. In that case, the value of gas constant will depend on how much water vapor exists in the air. So what is the concentration of water vapor in the air parcel that we are considering? How much percentage of it is occupied by the water vapor? So every time we change the water vapor concentration, the mean molecular weight for the moist air changes. If the mean molecular weight changes, the value of specific gas constant Rm also changes, which is basically the universal gas, the value of universal gas constant by the molecular weight of the air parcel that we are considering. So every time we change the water vapor concentration, the mean molecular weight of the moist air changes. So it will be difficult to find the value of Rm every time that we are considering a different moist air. So rather than using a different gas constant for each constitution of moisture, the gas constant for dry air is retained and a new fictitious temperature called as a virtual temperature is introduced. So instead of changing the value of R each time we are considering a moisture vessel, what we did was the value of R was retained and a new temperature, a new fictitious temperature, which is basically known as the virtual temperature, was introduced. So what is basically virtual temperature? So virtual temperature is the temperature that dry air would need to attain in order to have the same density as a moisture at the same pressure. Suppose if we have a dry air parcel and a moist air parcel, so these two are there at the same pressure and temperature. This is dry and this is moist. So basically the dry air parcel will have I was just going through the virtual temperature that we were discussing in the last class. So as we discussed earlier, virtual temperature is the temperature that dry air would need to attain in order to have the same density as the moisture at the same pressure. So these things we already discussed in the last class. We told that when we consider dry air and moisture, the dry air will be having higher density compared to that of the moisture. So if we want to make the density of both dry air and moisture same, we will have to increase the temperature of dry air. So the amount of the temperature to which the dry air should be increased to attain the same density as the moisture is basically known as the virtual temperature. And we also discussed that the virtual temperature is actually greater than the actual temperature that we are considering. And this, and I also told you that this is the equation for the virtual temperature. This Tv is equal to T by 1 minus E by P into 1 minus X. So today we will start with deriving this equation for the virtual temperature. Okay, so we are familiar with the ideal gas law. In case of dry air, we have PD equal to rho D RD into T. And for water vapor, in case of water vapor, the pressure, which is vapor pressure, is denoted by E, and the density rho V into RV into T. So RD is having a value of 287 and RV is that of water vapor is 461. These things we are already familiar. So now we are considering a moisture parcel which is having dry air plus some amount of water vapor. Okay. So consider a volume V of the moisture parcel. Consider a volume V of the moist air parcel. M mass of the moisture is given by Md plus Mv, which is the mass of dry air plus the mass of water vapor, and the density of the moisture will be given as rho d plus rho d. Density of dry air plus density of both dry air and water vapor are occupying the same area. We can write rho is equal to rho d plus rho v. Now from ideal gas law, rho can be written as rho d can be written as, from this equation we can write rho d is equal to Td by Rd into T. Td by Rd into T plus, and the density of water vapor can be written as E by Rd into T. Now the pressure Pd is basically Pd, which is the pressure exerted by dry air, is basically total pressure minus the vapor pressure. Pd can be given by P minus E. If we substitute that, we can write rho is equal to P minus E by RdT plus E by RV, which will become P by RdT minus E by RdT into 1 plus 1 by Rd by RT. If you take E by RdT common from the second and the third term, this will become P by RdT minus E by RdT into, this will be since we are taking minus E by RdT common, so inside the bracket it will be minus. It will be 1 minus, we know the value of Rd, we know the value of Rv, so we can calculate Rd by Rv, right? Rd is 287, whereas Rv is 461. What will be the value of Rd by Rv? What will be Rd by Rv? 287 by 461, right? How much it will be? It will be 0.622. This value Rd by Rv, this ratio Rd by Rv is denoted as epsilon basically. So it will be epsilon is equal to 0.622. So we can substitute it over here, which is 1 minus epsilon. Rd by Rv can be written as 1 minus epsilon. So rho is equal to P by Rdt minus E by Rdt into 1 minus epsilon. Now P can be written as This rho can be written as P by R dt. If we take P by R dt to this side, we can write the equation in the form rho plus P by R dt into 1 minus x, which is equal to rho R dt plus E into 1 minus x, right? P is equal to rho R dt into 1 plus if we take rho R dt common, it will be 1 plus E by rho R dt into 1 minus epsilon, which is equal to rho R dt into 1 plus E by rho by R dt is basically pressure into 1 minus epsilon. So P is equal to, now we got P is equal to rho R d T V, where TV is equal to T into 1 plus E by P into 1 minus epsilon. This is basically the equation for the partial TV is equal to T into 1 plus E by P into 1 minus epsilon. P is equal to rho R d TV is the ideal gas equation for moisture. That we have RD, and instead of that we are retaining the value of specific gas constant for dry air, and then we are introducing a new temperature which is known as a virtual temperature, which is given by TV is equal to T into 1 plus E by P into 1 minus. So this is how this is the equation for the virtual temperature. So as we already told, virtual temperature is the temperature that a dry air would have if its pressure and density were equal to that of a given sample of moist air. Okay, I think the derivation is clear. Now we will try to solve one or two problems. The first question, if the mixing ratio of an air parcel, if the mixing ratio of an air parcel is 2 gram per kilogram and the pressure is 1020 millibar, then what will be the vapor pressure? So the question is, if the mixing ratio of an air parcel. So mixing ratio will be a term which is not familiar to you. Mixing ratio is basically denoted by small r. Mixing ratio is defined as the mass of mass of water vapor to the mass of dry air. This is mixing ratio. If we take an air parcel, the ratio of the mass of vapor to the mass of dry air in that mass air parcel is known as mixing ratio. So in the question, so it basically shows this much water vapor is present in this much in a mass air parcel, this much water vapor is present for this much kilogram of dry air. So that's what it basically gives you how much water vapor is present in that. So that is mixing ratio. So mixing ratio is given as 2 gram per kilogram, which means in 1 kilogram of the ratio between the mass of vapor and mass of dry air is 2 gram per 1 kilogram of dry air. For every 1 kilogram of dry air, there is 2 gram of water vapor present. That's what basically this tells. So R is given as 2 gram per kilogram, and the pressure, which is the total pressure P, is given as 1020 millibar. What will be the vapor pressure E? That is the question. So this is the total pressure. We have to find the vapor pressure, which is E. So basically, we want to find the vapor pressure, which is E. So mixing ratio and total pressure is given in the question. So R is given by mv by mv, right? So we are considering same if the both moisture and dry air, the water vapor and dry air are occupying the same volume, we can write it as rho v by rho d as well. Density of vapor to the density of dry air. R can be written as rho v by rho d. R is given as 2 gram per kilogram or 0.002 kilogram per kilogram. This is the value of R. So from R is equal to rho v by rho d, we can write from ideal gas equation we know P is equal to rho d RD into T. TD is equal to rho d RD into T, and E is equal to rho v RV into T. If we substitute rho d and rho v from this, we can write R is equal to rho v will become E by RV into T into RD is basically RD T by T. Rho d is basically RD T by T. T is constant, so it will reduce to temperature is a constant, so we can write mixing ratio R is equal to E by RV into RD by Pt. So we know the value of RD by RV, right? E by Pv into RD by R, or it can be written as E by Pd into Epsilon. The mixing ratio R can be written as E by Pd into Epsilon, where Pd again can be written as P minus E. Is the total pressure minus the vapor pressure into epsilon. We know what is the value of P. So R is 0.002 kilogram per kilogram, and pressure is given as, what was the value of pressure? Pressure is given as 1020 millibar. 1020 millibar or hectopascal. So R, so 0. After substituting 0.002 is equal to E by 1020 minus E into 0.622, which is the value of epsilon. Epsilon is equal to 0.62. Now, can we calculate the value of E from this? We will take this here. It will become 0.002 into 1020 minus E is equal to 0.622 into E, which will be, can you solve and tell the value of E? Solve the equation and tell me the value of E. you get the value of P. Are you getting the value of P? The value of E will be 3.26 hectare pascal. You are able to get the value. It will be around 3.26 hectare pascal. This is the value of vapor pressure. Now we learned a new term which is known as a mixing ratio, right? Mixing ratio is given by mass of water vapor to the mass of dry air. Now let's try to solve another question, which is, so the answer to the previous question is 3.26 hectopascal. Okay, the value of vapor pressure is 3.26 hectopascal. Now next question, Q is equal to, sorry, not Q. The next question, if specific humidity of a sample of air is 0.0196 at a temperature of 303 Kelvin, find the virtual temperature. What is virtual temperature? Virtual temperature is the temperature that a dry air would have if it was at the same density of that of the moisture, at the same pressure. Find the virtual temperature if total pressure P of the moisture plus 1014 hectopascal. What is its density? Okay, so the first part of the question, specific humidity of a sample of air is given. So this is again a new terminology, specific humidity, which is denoted as Q and is defined as the mass of water vapor to the total mass of air. Q is given as mV by mV plus mV, where mV is the mass of vapor in the given moisture parcel divided by the total mass of moisture, which is mV plus mV. mV by mV plus mV is what is known as specific humidity. The value of specific humidity is given as 0.0196 kilogram per kilogram. Unit is not given, so it will be kilogram per kilogram. And the temperature is given as 303 Kelvin. So the first part is to find the virtual temperature PV. So PV is basically T into 1 plus E by P into 1 minus epsilon, right? We just derived the equation. So we know what is the value of P, which is 1014 hectopascal, but we don't know what is and we know T also. T is 303 Kelvin. The only unknown quantity in the equation is E, which is the vapor pressure. We don't know the value of vapor pressure. So first we have to find the value of vapor pressure and then we can find Australian pressure. So what we have is the value of specific humidity. So from the value of specific humidity, we have to find the value of vapor pressure. The specific humidity, as I told, is defined as mv by mv plus mv. So from this we can write specific humidity Q as rho V by rho V plus rho V. Again, from the ideal gas equation, rho V can be written as E by RV into T. And rho D can be written as P by PD by RV into T. So it will become Q is equal to rho V is E by RV into T by E by RV into T plus PD by RV into T. From here, T is common, like the value of T is same. So Q will become E by RV by E by RV plus PD by RV. From this we can take RV as common. So it will become Q is equal to 1 by RV. Again in the denominator 1 by RV will come. So this will eventually cancel out. If we take 1 by RV common, it will become E by E plus, here if we take 1 by RV out, it will become RV PD by R. So it will be Q is equal to E by E plus, what is RV by RD? RV by RD can be written as one, it will be epsilon into T. It will be P by epsilon. Because RD by RV is epsilon. Here it is RV by RT, right? So it will be 1 by epsilon. So it will become E by E epsilon plus PD E epsilon. E into epsilon by E epsilon plus P minus E. So PD can be written as the total pressure minus the vapor pressure, right? Will eventually reduce to 0.622 epsilon, 0.62, which is E into epsilon by P minus after. So it will eventually reduce to Q is equal to 0.622 E by P minus E. So now from since we have the value of Q, we can calculate E from this equation, right? So Q is we got Q is equal to 0.622 E, which is vapor pressure, divided by P minus E, right? So we know the value of Q, which is given as 0.0196. So 0.0196 is equal to 0.622 into E. Pressure, the total pressure, the value of total pressure is also given as 1040 minus. So we calculate 0.0196 into 1040 minus E is equal to 0.622. So it will become 19.87 minus 0.0196 E is equal to 0.622, or 19.87 is equal to 0.622 plus 0.0196 will be 0.6416 E. So E will eventually become 19.87 divided by 0.6416. How much it will be? What will be the value of E? 19.87 divided by 0.6416 will give you a value of 30.96. 30.96 hectopascal. This is the value of vapor pressure. I hope you got the answer. Okay. So the value, the answer is 30.96 hectopascal. So we have found the value of E. The question was to find the value of virtual temperature, right? So since now we have the value of vapor pressure from the equation, TV is equal to T into 1 plus E by P into 1 minus epsilon. We can find the value of TV. So we know the value of T, which is 303 Kelvin, into 1 plus the value of E we just now found out, which is 30.96, divided by the value of P is given in the question, which is 1040, into 1 minus the value of epsilon we know, which is 0.62. So can you compute and tell me what will be the virtual temperature, the value of virtual temperature, TB. The value of virtual temperature TB will be you get try to solve the equation. I am getting a value of around 306.49 Kelvin. This is what I am getting, 306.49 Kelvin. Just check and let me know if it is correct or not, if you are also getting the same value. Okay, so we found the virtual temperature. Now what else was there in the question? A specific humidity of a sample of air is 0.016 at some temperature, at the temperature of 303 Kelvin. Find the virtual temperature, that we did. Now the total pressure of the moisture is 1014 hectopascal. What is its density? The second part of the question is to find the second part of the question is to find the density of the moisture pascal. Rho. We know P is equal to rho R D PV, right? This is the equation, ideal gas equation for the moisture pascal, where we are retaining the value of specific gas constant of dry air RT and replacing the actual temperature with the virtual temperature T. Now we know the total pressure is 1014 hectopascal is equal to rho into the value of RD is 287. We know the value of virtual temperature, which is 306.5. Now the value of rho is basically 1040 divided by 287 into 306.5. What it will be? 1040 divided by 287 into 306.5. The value of pressure is in hectopascal, so you have to convert it into pascal, which is 1014 into 10 square. How much it is? It is coming around 1.15 kilogram per meter cube. The value of pressure is in hectopascal, so you have to always convert it into pascal. Earlier we didn't convert it because here we are taking a ratio of vapor pressure and the actual pressure. So since both are in hectopascal, it will eventually cancel out. And here also, while calculating the value of vapor pressure, also we took the total pressure 1014 hectopascal only. That's why we got the value of vapor pressure in terms of hectopascal. But here we are calculating density, so pressure has to be converted into. So it is always better to convert it into pascal and then use the equation to avoid mistakes. Okay. So the answer is 1.15 kilogram per meter cube. I hope you got the answer. I hope the concepts are clear. Yeah. Yeah, Soumya, the value is coming at 0.011. So that's what I was telling. You have to calculate, you have to convert the value of pressure from hectopascal to pascal, which is in SI unit. So then calculate. So you will be getting around 1.1, 1.1 kilogram per meter cube is the answer. Okay. So I basically introduced three new terms. The first one was a virtual temperature. So we are using virtual temperature in case of moisture pascal in order to retain the value of RD in the ideal gas equation. So PV is given as T into PV is given as T into 1 plus E by P into 1 minus epsilon. And the ideal gas law for a moisture pascal is given by R is equal to rho D T. And we learned what is mixing ratio of an air pascal. Mixing ratio is given by mv by mv. mv is the mass of vapor. Mass of water vapor. md is the mass of dry air. And in terms of pressure, we derived an equation. During the problem, we found that mixing ratio can be written as E by T minus E into epsilon. R is equal to the ratio of Uh, it can also be written as a ratio of vapor pressure to the ratio of pressure of dry air into epsilon. And specific humidity, we also learned what is specific humidity Q, which is mv by mv plus mv. This also in terms of pressure can be written as E into E by P minus E into epsilon. Similarly, Q can also be written in terms of pressure as E by P minus E into epsilon. Okay, two new terms we learned. One is maximization, one is the specific humidity, which is mv by mv plus mv. Okay, so now we will move on to the next topic, which is the first law of thermodynamics. So we know that in addition to the macroscopic kinetic and potential energy that a system possesses as a whole, it also contains internal energy. So we know like a system will be having, you are familiar with the term internal energy, right? You would have learned in your college. So a body, in addition to its macroscopic kinetic and potential energy, it also possesses an internal energy, which is due to the microscopic kinetic and potential energy of the system, or the kinetic and potential energy of its molecules or atoms. The microscopic kinetic and potential energy of the molecules or atoms are basically known as the internal energy of the system. Suppose consider a closed system of unit mass. If an amount of, I'll just before going to that. So internal energy. So if a system, if it is at rest, it will have a potential energy. If it is moving, it will have a kinetic energy. So the system will also possess, in addition to the macroscopic kinetic and potential energy, the system also possesses an internal energy, which is due to the microscopic kinetic energy and potential energy of the molecules and atoms which the system composes basically. So the kinetic energy is basically due to the movement of atoms or molecules, the constant movement of atoms or molecules within the system. Within the system is the kinetic energy, and potential energy is basically the energy that is used to. Potential energy is due to the intermolecular forces, intermolecular or intramolecular forces that is which is basically there within the system. So that is the internal energy. So consider a closed system of unit mass. If an amount of heat Q, suppose there is a closed system which is having unit mass, and we are supplying an energy Q, a heat Q to the system. The system may do a certain amount of external work, and the remaining energy will be used partly in increasing the temperature or partly in overcoming the force of attraction between the molecules, which basically is the internal energy of the system. So suppose we are giving a heat Q to the system. A part of this heat Q will be used to do some external work, which is represented by W, and some of it will be used to in increasing the internal energy of the system. Internal energy means it could either be used to increase the kinetic energy of the molecule, which will basically result in change in the temperature of the system, or it will be used in overcoming the force of attraction between the molecules, which is basically the change in the microscopic potential energy of the system. So if you supply a heat Q to a system, either it will be used to do an external, a part of it will be used to do an external work, and a part of it will be used in changing the internal energy of the system. So if we write this equation in differential form, we can write dQ is equal to U plus W. In differential form can be written as dQ is equal to dU plus dW, where dQ is the amount dW is the work done. Now let's just try to do a problem from this equation. So calculate the work done in compressing dry air of 2 kg to half of its initial volume. So mass is given as 2 kg and the change in the volume V2 is V1 by 2. So V1 is the initial volume and V2 is the final volume. Then it is given that V2 is equal to V1 by 2. It is the final volume is half of its initial volume. And the temperature is given as 0 degrees Celsius or 273 Kelvin. So we have to basically find the work done. The work done dW given by P into dV. This is basically pressure volume work. So change in work done is given by pressure into change in the volume. So we don't know the value of P. We do know the value of dV, which is it has changed from V1 to V1 by 2. So from the ideal gas flow, we can write PV is equal to mRD. This is the same as PV is equal to nRT. Instead of the number of moles, we are using the mass of the gas that we are consuming. So it will be PV is equal to mRD. We know the value of m, which is 2 kg. We know the value of RD, which is 287. We know the value of P, which is 270. Now this, if we substitute, we will get dW equal to PdV. From the ideal gas equation, we will get what is P. So P will be m into RdT by V. So dW will be mRdT by V into dV. So we want to calculate the work done. So W, the work done, integral V1 to V2 dW is equal to mRdT into integral V1 to V2 dV by V. So this W will be mRdT integral dV by V will be log of V2 by V. So 2 into 287 into 273 into log of V2 is V1 by 2. It will be log of 0.5. Log of 1 by 2 or log of 0.5. What will be the work done? Can you tell me how much it will be? 2 into 287 into 273 into log of 0.5. What will be the work done? How much you are getting? The value of work done. Two into 287 into 273 into log 0.5. How much it is? Yes, minus 0.10867. That is the answer. So the answer will be minus 108,671, right? Minus 108,617. Minus 108,617 joule. Or we can write it as minus 108,617 kilo. We are getting negative because here the work done is to compress the system. So since compression is happening, the work done will be negative. If there is expansion, the work done will be positive. So that is the first law of thermodynamics. So this is the work done. Now let's see another important parameter, which is known as specific heat. So suppose a small quantity of heat dQ is given to a unit mass of material, and as a consequence of the supply of the heat, the temperature of the material increases from T to T plus delta T plus dT without any changes in the phase occurring within the material. That is, there is no change of phase like from water to ice or ice to solid to liquid, gas to liquid. No phase changes are occurring. The energy that is being supplied is just used to increase the temperature of the material. So the ratio dQ by dt is called the specific heat of the material. Okay. Suppose we are supplying a heat. Suppose if we are supplying a small quantity of heat dQ to the system, we supply the heat, the temperature of the system increase from T to T plus dt. Then the ratio dQ by dt is known as the specific heat. The amount of dQ by dt is basically specific heat. So specific heat can occur at constant volume and constant pressure also. Suppose if when we are supplying the heat, there is no change in the volume that is occurring to the system. Then in that case, the heat supplied is known as the specific heat at constant volume, which in case of dry air is having a value of 716 joule per Kelvin. And suppose if we are supplying the heat at constant pressure, which means the pressure of the system is not changing, and we are supplying the heat. There is no change in pressure that is occurring to the system. Then in that case, the specific heat for dry air is having a value of 1004 joule per Kelvin. So as we can see here, the value of Cp is greater than Cv. The value of Cp, which is 1004, is greater than the value of Cv, which is 717 joule per Kelvin. So why Cp is greater than Cv? So we know from the first law of thermodynamics that dQ is equal to dU plus dW. And dW is basically the pressure volume work, so it can be written as PdV. Okay, so dQ is equal to dU plus PdV. This is the first law of thermodynamics, right? So suppose when we are supplying the heat, which is dQ, we are supplying a constant volume. So if we are supplying the heat at constant volume, then dQ, then dV will be 0. This quantity dV will be 0 if we are supplying it at constant volume. We are telling like the heat that we are supplying is not used to create any change in the volume of the system. So in that case, dQ will be used solely to increase or change the internal energy of the system. So it will attain a higher temperature faster. Since there is no work done, the heat is not utilized to do any work by the system. The entire energy that we are supplying is used to increase the internal energy of the system. So it will reflect in the temperature faster. Now suppose, so the purpose is to increase the temperature, right? So whatever the heat we are supplying is only used to change the internal energy, we will be able to change the temperature faster. And if we are supplying it at constant pressure, which means dQ is dU plus PdV. So in that case, the dQ supplied, some of the energy heat is used to change the internal energy, which will reflect as a change in temperature, and some is used to do some work as well. So in that case, since the energy is getting divided, we have to supply more amount of energy to the system to see a change in temperature. So that's why specific heat of at constant pressure is greater than the specific heat at constant volume. And another Cp is greater than Cv in case of dry air. Another important aspect is that can you compute the value of Cp minus Cv and tell me what is the value? What is the value of Cp minus Cv? Can you tell me what is the value of Cp minus Cv? Cp is 1004 and Cv is 717. So one thing is Cp is greater than Cv. Another interesting factor is find the difference between Cp and Cv and you will be able to find it. Can you tell me what is the difference? 1004 minus 717, how much it will be? Yeah, 287. What is 287? Have you seen this value before? What exactly is 287? Does it remind you of some term, some constant? Yes, Sujata. What is 287? Are you familiar with this value? Does it remind you of something? Yeah. 287 is basically RT. Cp minus Cv is basically R. So that is another important relationship. Okay. The specific so Cp minus Cv is given by R. Suppose a small quantity dq is given to a unit mass of the material. And as a consequence, the temperature of the material rises from T to D plus dt without any change in phase of the material. The ratio dq by dt is called as the specific heat of the material. And the heat that we are supplying could be at constant volume or at constant pressure. So if we are supplying the heat at constant volume, the amount of heat that will be required to increase the temperature is 717 joule per Kelvin. And if we are supplying it at constant pressure, then the amount of heat that is required to raise the temperature will be 1004 joule per Kelvin. So Cp is greater than Cv because when we are supplying the heat at constant volume, the amount of heat that we are supplying is solely used to change the internal energy of the system. dq will reduce to du. Whereas in case of constant pressure, dq is du plus pdv, which means some of the energy is used to change the internal energy of the system, whereas the remaining is used to do some external work. That's why Cp is greater than Cv. And when we found the difference between Cp and Cv, we found that the value is equal to RT, or the specific gas constant for dry. Now let us see the different forms of thermodynamic equation. So dq is du plus pdv or pd alpha, which we are already familiar with. dq is equal to du plus dw. dw is pdv or pd alpha. So dq can be written as du plus pd. This is the first form of thermodynamic equation. Now dq is equal to cd dt plus pd alpha. This is another form of thermodynamic equation in terms of the specific heat constant at constant volume. And in terms of specific heat at constant pressure, we can write dq is equal to cp dt minus alpha dt. So these are the three different forms of thermodynamic equation. The derivations are there in the actual NPTEL class. You can look at it. I don't want to repeat the same thing. The specific heat of a gas is a quantity of heat required to raise the temperature of unit mass of gas by 1 degree. So the change in temperature will be basically 1 degree. Suppose if we have some material which is such a degree, some system which is having a temperature of 25 degrees Celsius, we have to increase the temperature of the system from 25 to 26. So dt is 1 degree Celsius. How much energy we should supply to the system? That's what specific heat basically tells us. The specific heat of the gas is the quantity of heat required to raise the temperature of unit mass of gas by 1 degree. We want to get the increase in temperature by 1 degree. How much heat we should supply to the system? That's what specific heat basically tells you. Think you are now you know what is specific heat. Now let's look at another important parameter, which is enthalpy. Suppose if we are adding heat to a material at constant pressure, so that the specific volume of the material increases from alpha 1 to alpha. volume is basically the volume corresponding to 1 kilogram of a substance. The volume corresponding to 1 kilogram of a substance or a material. The volume is basically alpha or specific volume. It is defined as 1 by rho. So suppose if we are adding heat to a material at constant pressure, so that the specific volume of the material changes from alpha 1 to alpha 2. So the work done by unit mass of the material is given by, so dW is PdV. So if we are considering 1 kilogram of the material, we can write dW is equal to PD alpha. So suppose if we are changing alpha 1 to alpha 2, then the work done dW can be written as P into alpha 2 minus alpha 1. Right? So P into alpha 2 minus alpha 1. Therefore, the finite quantity delta Q added to the material, if suppose U1 and U2 are the initial and final internal energies of the material, then delta Q, so this is dW, delta Q or Q we know as U plus W, right? So delta Q can be written as the internal, if we supply heat Q to the system, the internal energy will change from U1 to U2, so it will be U2 minus U1 plus W will change from W2 to W1 or P into alpha 2 minus alpha 1. So delta Q can be written like this. Delta Q is equal to U2 minus U1 plus P into alpha 2 minus alpha 1. Or delta Q can be written as U2 plus P alpha 2 minus U1 plus P alpha 1. This is like we can just rearrange the equation and we will get this. Delta Q is equal to U2 plus P alpha 2 minus U1 plus P alpha 1. We just rearrange based on the subscripts that we have. And this quantity U plus P alpha is the enthalpy of the system, which is denoted by H. So delta Q can be written as H2 minus H1, where H is equal to U plus P alpha. This is the enthalpy of the unit mass of the material or the system. So what we did, we are adding some amount of heat to a system, so that the specific volume of the system increases from alpha 1 to alpha 2. So the work done, which is PD alpha, is given by P into alpha 2 minus alpha 1. Suppose Q is the amount of heat that we are supplying to the system. Then delta Q will result in a change in the internal energy, and it will also do an amount of work which is given by P into alpha 2 minus alpha 1. The first law of thermodynamics can be written as, which is Q is equal to U plus W, can be written as delta Q is equal to change in the internal energy, which is U2 minus U1 plus P into alpha 2 minus alpha 1, which is the work done. So now, if we rearrange it based on the subscripts, which is all subscripts with 2 together, then it will become delta Q is equal to U2 plus P alpha 2 minus U1 plus P alpha 1, or delta Q can be written as H2 minus H1, where H is the enthalpy of the material, which is given by H is equal to U plus P alpha. So that is enthalpy. Now if we are differentiating H is equal to U plus P alpha, or the enthalpy of the system, we will get dH is equal to du plus d of P alpha. So we got H is equal to U plus P alpha. Now if we are differentiating it, it will become dH is equal to du plus d of P alpha. Now we substitute from the first law of thermodynamics, we can write dQ is equal to du plus pdf, right? Thus we can write du as dq minus pdl. We substitute that in the enthalpy equation. We will get dH is equal to dq minus pd alpha plus d of p alpha. This will become dH is equal to dq minus pd alpha plus d of p alpha is alpha d3 plus p plus and minus pd alpha will become dH will become dq plus alpha. This is the enthalpy of the system. dH is equal to dq plus alpha dT. Now, at constant pressure, we know the first law of thermodynamics can be written as dq is equal to dp dt minus alpha dp or dH. So, if we compare it with this, if we compare these two equations, dH is equal to dq plus alpha dp and dq is equal to cp dt minus. This can be rewritten as dq is equal to dH minus alpha dt. So, if we see these two equations, cp dt and dH are same, right? All other values are similar, dq minus alpha dt minus alpha dt. So, dH can be written as cp dt. So, dH can be written as cp into dt. Now, to integrate the equation, we will get h is equal to cp dt. So, the enthalpy h corresponds to the heat required to raise the temperature of a material from 0 to T Kelvin at constant pressure. So, at constant pressure, if we are raising the temperature of a material from 0 to T Kelvin, the amount of heat that we need, that is required, is known as the enthalpy. Okay, from there, so we started from the first law of thermodynamics. Initially, we found H is equal to U plus P alpha, and dH is equal to du plus Pd alpha, d of P alpha. Then from there, we understood, we got dH is equal to Cp dt, and after integrating, H is equal to Cp into T. So basically, enthalpy corresponds to the heat required to raise the temperature of a material from 0 to 2 Kelvin at constant pressure. So that is enthalpy. So we first we learned what is the first law of thermodynamics, which is Q is equal to U plus W, where W is P d alpha. W is basically the pressure volume work. So dW is equal to P d alpha or P dV. And we found three different forms of thermodynamic equation. First one is dQ is equal to du plus Pd alpha. Second one is dQ is equal to, in terms of specific heat at constant volume, Cv dt plus Pd alpha. And in terms of specific heat at constant pressure, we found dQ is equal to Cp dt minus alpha dt. So three different forms of, I'll just write it down. Different forms of first law of first law of thermodynamics basically just tells you if we supply a heat Q to a system, the amount of heat will be used partially to increase the internal energy of the system, and the other part will be used to do some external work. So the basic formula dQ is equal to du plus dW. Since dW is P d alpha, we can write dQ is equal to du plus P d alpha. Okay. Now at in terms of this is the first one. Now in terms of specific heat at constant volume, we can write dQ is equal to Cp specific heat at constant pressure can be written as PQ is equal to CP minus alpha T. In terms of enthalpy, we can write PQ is equal to VH minus alpha T. So these are how many forms are there? 1, 2, 3, 4, 5. 5 different forms of thermodynamic equation. And what is specific heat? Specific heat is the amount of energy or the amount of heat supplied to a material to raise the temperature of it by 1 degree Celsius without any freeze. Yeah. That is specific heat. Now what is enthalpy? Enthalpy is the amount of energy supplied to a system at constant pressure to raise the temperature from 0 to peak Kelvin. H is given by Cp. Enthalpy is the amount of energy or the heat supplied at constant pressure to increase the temperature from 0 to 2 Kelvin. That is enthalpy. H is given by Cp into T. And at constant volume, the first law of thermodynamics reduces to dQ is equal to dQ. Specific heat dQ by the ratio dQ by dt is known as the specific heat. dQ by dt is equal to Cv in case of constant volume. So dQ is equal to Cv dt. Okay, in case of constant volume. So yeah, those are the different forms of thermodynamic equation. You know what is specific heat now? Specific heat is dQ by dt, the amount of heat supplied to a system to increase the temperature of a system by 1 degree Celsius. And enthalpy is the amount of heat supplied at constant volume to a system to increase the temperature from 0 to 2 Kelvin. That is enthalpy. Now we will look at another important concept, which is the dry static energy. Dry static energy of an air mass. What do you mean by dry static energy? Let's have a look at it. Just a second. Now let's look at what does it mean by the dry static energy of an air mass. So we just found the enthalpy of a system as H is equal to Cp into T. Right? From the geopotential equation, which we have already learned, if you remember, geopotential is the amount of work done to raise an air parcel of unit mass from sea level to a particular height. So d phi is given by g dz, which can be written as minus alpha dp. So minus alpha dp came from the hydrostatic equation. Just dp by dz is equal to minus rho. As I told you earlier, alpha is basically 1 by rho. We can write, or rho is equal to 1 by alpha. We can write dp by dz is equal to minus g by alpha, or minus alpha dP is equal to G dx. That's how it came. So d phi can be written as G d phi is equal to minus alpha dP. The first law of thermodynamics in terms of enthalpy is dq is equal to dH minus Cp dT. First law of thermodynamics in terms of enthalpy is dq is equal to dH minus alpha dP. So dq can be written as, from this equation, dq can be written as dH plus d phi, right? Suppose or dq can be written as d of h plus which is equal to d of h can be written as Cp d plus phi. Okay. This h plus phi, this quantity h plus phi is known as the dry static energy of an air pass. The quantity h plus phi is known as the dry static energy of an air pass. In an adiabatic process, which means, what does it mean by an adiabatic process? That no heat enters the system, right? So in the above equation, if we are considering an adiabatic which process, which term will become zero? Can you tell me? If we are considering an adiabatic process in which there is no heat entering or leaving the system, which means there is no heat supplied or there is no heat lost from the system, which quantity in the above equation will become zero? In case of an adiabatic process, which quantity will become zero in the above equation? Can you tell me? In the equation, dq is equal to d of h plus phi, which quantity will become zero if we are not supplying any heat to the system? Phi? Phi you are telling. How come phi will be? Okay. What is dq? What is q? What is q? Q or dq? What it is? No. Oh God. Okay. Okay. Oh, you are getting confused with Q that we were discussing earlier was specific humidity, but here the Q that I'm like implying is actually heat. Like we discussed in, like if we are supplying an amount of heat Q to the system. So here by Q I meant the heat supply to the system. Q was specific humidity when we were discussing the earlier problems. Okay, sorry that I didn't clarify that. Q is basically the heat supply to the system. U is the internal energy of the system and W is the work. Q is the heat. So when I'm telling we are not supplying any heat to the system and there is no heat leaving from the system, it means Q is zero. If we are not supplying any heat, the heat Q is basically zero. In here, the Q that I'm like mentioning is basically heat. It's not specific humidity. I'm sorry that I didn't clarify. So Q is basically the heat supply to the system. It's not specific humidity. Okay. Q is the heat supply to the system. So in an adiabatic process, when I'm telling that there is no heat supplied or there is no heat supplied to the system or there is no heat leaving from the system, it means the quantity Q will be zero. dQ will be zero. If dQ if here dq is equal to 0 in case of an adiabatic process, then h plus phi, d of h plus phi will be a constant. Sorry, d of h plus phi will be 0 and h plus phi will be a constant. D of h plus 5 is basically denotes the change in h plus 5. During an adiabatic process, since there is no heat being added or there is no heat leaving the system, dq will be 0, which means d of h plus 5 will be 0, which basically implies h plus 5 will be a constant. That is, the dry static energy of an air parcel will be constant. Suppose if you have some air parcel whose mass is fixed and it is moving in a hydrostatic atmosphere, an atmosphere which is in hydrostatic equilibrium, which means the equation dp by dz is equal to minus rho g holds true in the atmosphere. So suppose if you have an air parcel which is having a fixed mass m and it is moving in an atmosphere which is at hydrostatic equilibrium, which means dp by dz is equal to minus rho g holds true in the atmosphere. So we have an atmosphere which is in hydrostatic equilibrium and there is an air parcel whose mass m is fixed, which is moving in this atmosphere, and that the quantity which is given by h plus phi of the air parcel will be conserved. The dry static energy of the air parcel, the enthalpy and the sum of the enthalpy and geopotential of the air parcel will be a constant, provided the parcel neither gains nor loses any heat from the surroundings. That is basically known as dry static energy. H plus. Suppose we have an air parcel of fixed mass which is moving in an atmosphere which is at hydrostatic equilibrium. In that case, the quantity given by h plus phi, which is the dry static energy, is conserved. This is the dry static energy. Dry static energy is conserved given that neither heat enters the system nor leaves from the system. Which means the process, the vertical motion that is happening is basically an adiabatic process. Neither heat enters the system nor leaves the system. So what is meant by an adiabatic process? We already told. Yeah. So we have already discussed that if a material undergoes a change in its physical state, example pressure, volume, or temperature, without any heat being added to or withdrawn from it, the change is said to be adiabatic. So when we are saying that a process is adiabatic, it means no heat is added to the system or no heat is withdrawn from it. And in case of an adiabatic process, dq will be 0. dq, which is the amount of heat supplied to the system, q is the heat actually. So dq will be 0. In case of an adiabatic process, dq will be 0. And the first law of thermodynamics, which is dq is equal to du plus dw. dq is equal to 0, du will become minus pdi. So dw is pdi. du is equal to minus kd alpha. Suppose if we are considering an adiabatic compression in the sense V2 was less than V1, V1 is greater than V2. In that case, suppose we are doing the volume of the system is decreasing from V1 to V2. Then in that case, if V2 is less than V1, Pd alpha will be positive, and according to this equation, du will be if V2 is less than V1, then if V2 is less than V1, then PD alpha will be negative. Suppose if the volume is decreasing, if V2 is less than V1, then PD is not positive, it will be negative. So PD alpha will be negative, then according to the equation du will be positive, which basically if there is an increase in the internal energy, it will lead to an increase in temperature. Suppose when we are considering adiabatic expansion, which means V2 is greater than V1, then PD alpha will be positive, which means du will be negative, which basically implies there will be a decrease in temperature of the system. So in case of compression, in case of adiabatic compression, there will be an overall increase in the temperature of the system, whereas in case of an adiabatic expansion, there will be an overall decrease in the temperature of the system. Okay. Now let me introduce you the concept of an air pass. Generally, when we talk about the vertical motion in atmospheric science, we generally use the term air pass. So the system that we generally consider in case of atmospheric science is an air pass. So what basically is an air pass? So air parcel is basically just like for easy to imagine, you can consider just a cube of air in the atmosphere, which has a fixed volume and fixed mass. It has a fixed volume and fixed mass. So that is basically an air parcel. So this air parcel is suppose it is moving vertically in the atmosphere. So in the atmosphere, all mixing in the vertical is accomplished by the exchange of macro scale air parcels, which means it doesn't undergo microscopic exchange. The identity of the parcel will be intact. So all mixing will be macroscopic, and the parcel will be thermally insulated from its environment, so that the temperature changes adiabatically. As the parcel rises or sinks in the atmosphere, the temperature of the air parcel will change adiabatically. There won't be any, which means there won't be any additional from the surroundings. There won't be any addition of heat, or um, there won't be any. The system will never. The system won't release any energy to the surroundings, or it will not gain any heat from the surroundings. So it will always be thermally insulated from its environment. So whatever temperature changes occurring, it will be basically adiabatic in nature. The third one, it always remain at exactly the same pressure as the environmental limit. So if we say that an air parcel is having a pressure of 600 hectopascal, it means that it is at a level of 600 hectopascal level in the atmosphere. So the surrounding and the parcel will be having the same pressure. And it is always assumed to be in hydrostatic equilibrium, which means the equation dP by dz is equal to minus rho g will always be held true in case of an air parcel. And as a parcel slowly moves in the air, it is considered that the macroscopic kinetic energy of the parcel is negligible compared to that of the total energy. So we doesn't consider, because since it is moving very much slowly, we doesn't consider the macroscopic kinetic energy of the parcel, which is basically considered to be negligible. So these are the basic assumptions that we have when we are considering an air parcel, but when we consider the vertical movement of air parcel in the atmosphere. Now let's calculate the rate of change of temperature with the height of a parcel of air. Suppose we have a parcel of air. Suppose if we have a parcel of air which is moving up in the atmosphere, we are going to find how is the temperature of the parcel changes with respect to height. Okay, so we are basically going to find out dP by dz. So we just now we found that just now we've learned that As the parcel is moving in the atmosphere, the parcel is thermally insulated from its environment. So no heat either enters or leaves the parcel, which means the processes are adiabatic, which means dq is equal to 0. This is the first assumption. And we also found that the parcel will always be hydrostatic equilibrium, which means dp by dz is equal to minus rho g. This will always be held true for the parcel. So these are the two assumptions when we are considering a parcel. So dq is equal to 0, then we can write dq is equal to d of h plus phi. This is the dry static energy. For d is equal to cp t plus phi is equal to 0. Cp t plus phi is equal to, or if we just open, so in case of an adiabatic process, we know dq is equal to 0, which means d of h plus phi is equal to d of cpt plus phi is equal to 0. From d of cpt plus phi is equal to 0, we can write cp dt plus d phi is equal to 0. Or we can write cp dt is equal to minus d phi. Now basically we want to calculate what is dt by dz, right? So just divide the whole equation by tell you once more. So the first assumption is dq is equal to 0, since all atmospheric motions and processes are considered to be adiabatic. This is the first assumption. And the second assumption is the parcel will always be in hydrostatic equilibrium, which means dp by dz is equal to minus rho g. So since dq is equal to 0, we can write dq is equal to d of h plus phi, which is equal to d of cpt plus phi is equal to 0. So if we open the bracket, cp dt plus d phi is equal to 0, or cp dt is equal to minus d phi. If we divide the whole by dz, we will get cp into dt by dz is equal to minus d phi by dz. If you remember the geopotential d phi is defined as minus g dz. So if we substitute it over here, we will get cp into dt by dz is equal to minus g dz by dz. dz and dz will be cut off. Then c dt by dz will be minus g by c. So this gives you the rate of decrease in temperature with respect to height of an air parcel. So you know the value of g, right? G is having a value of 9.8, and cp is having a value of, we already calculated, it is what was the value? cp 1004, I guess. Yeah, cp is having a value of 1004 in case of dry air. Now can you calculate the value of dt by dz? What will be the value of dt by dz? G by cp it is. How much it will be? 9.8 divided by 1004. What will be the value of g? What will be the value of g by cp? 9.761. But it will be minus value of dt by dz will be around minus 9.76 into 10 raised to minus 3 is also there, right? This will be 0.009 degrees Celsius per will be 0.009 degrees Celsius per meter. So this much it will change as we into 10 raised to minus 3 is also there, right? 9.8 divided by 1004 is 9.761 into 10 raised to minus 3. So that is the value of G by Cp or dT by dZ. It basically gives you how the temperature is changing as we move, as we vertically move in the atmosphere. Okay, and don't confuse it Q with the Q that I'm talking about is here. The Q that I'm talking about is the heat.
This question is ma'am.
Yeah.
Its value is 0.009 degrees centigrade per kilometer or meter.
It will be per meter.
Okay.
Yes.
Thank you.
9.8 divided by 1004, right? It is into 10 raised to minus 3 is coming, right?
Perhaps in
Yeah, that's
video,
what I was also.
real video,
Yeah,
yes,
it
it
is
is
per kilometer.
0.00098 Kelvin per meter.
Yeah, 0.9009 Kelvin per meter, right?
Yes, yes. And in kilometer, it is 9.8 Kelvin per kilometer.
Yeah, it is in meter, it is not in kilometer.
Yes.
0.0096 degrees Celsius per meter.
It
Everything,
is
this is meter per second square. This, the unit of Cp is joule. It is joule per Kelvin.
it is madam Kelvin per meter.
It can be Kelvin
Written in
or
terms of
degree
Celsius.
Celsius. Yeah, both are correct actually
Okay, okay,
because it
okay.
is just a difference in temperature.
Okay.
So if it is in degree Celsius, since it's the difference, both are correct. It can be
Got it.
Kelvin also or degree Celsius also.
And in per kilometer, it is 9.8
Yeah, yeah.
Kelvin degree
Yeah,
centigrade.
yeah. If
Meter.
you convert, so this is basically in meter.
Yes.
If you convert it into kilometer, which is into 10 raised to 3, if you do, you will get in terms
Okay.
of kilometer, which is 9 degrees Celsius or 9 Kelvin per kilometer. Both are correct.
Thank you. Thank you, madam.
Yeah. So it is 0.009 degrees Celsius per meter or 9 degrees Celsius per kilometer. Or Kelvin. Kelvin is also correct. So yeah, that is the dry adiabatic lapse rate, which is dT by dZ. I hope the things are clear. So we learned a lot of new terms today. First one was we learned what is virtual temperature, which is basically the temperature that a dry air parcel would have if it has the same density of that of moisture air parcel. And we derived the equation PV is equal to T into 1. Yeah, PV is equal to T into 1 plus E by T into 1 minus epsilon. And in case of a moisture air parcel, the ideal gas equation becomes T is equal to rho RD into TB. We are retaining the value of specific gas constant dry air and changing the actual temperature to virtual temperature. Then we learned what is mixing ratio, which is R, small r denoted by small r, which is given by mass of vapor by mass of dry air. Then we learned what is specific humidity, which is denoted by small q and is given by mv by mv plus mv, mass of vapor to the total mass of the moisture air parcel. Then we learned what is the first law of thermodynamics, which is q. If you supply an amount of heat q to a system, part of the energy will be used to increase the internal energy of the system, and the The remaining will be used to do an external work. So that is first law of thermodynamics. Then we learned water specific heat, the value of specific heat at constant volume and the value of specific heat at constant pressure. We also learned Cp is greater than Cv and Cp minus Cv is given by R. So specific heat is the amount of heat required to increase the temperature of a system from by 1 degree Celsius. 1 kilogram, like unit mass of a system from unit mass of a system by 1 degree Celsius. That is specific heat. And we learned what is enthalpy, which is the amount of heat supplied at constant pressure to increase the temperature from 0 to T Kelvin of T degree Celsius. So that was enthalpy. And we learned what is dry static energy, which is given by H plus phi. And we also learned that in case of atmospheric motions, which are adiabatic and always maintain hydrostatic equilibrium, this quantity H plus phi is always conserved. Then finally we also learned, and we learned what are the properties of an air parcel, and then finally we learned what is the rate of change of temperature with respect to height, dT by dz, which is given by G by Cp, and we got the value as 0.009 degrees Celsius per meter or 9 degrees Celsius per kilometer. This quantity is known as the dry adiabatic gas. I think that is enough for today. If you have any doubt, you can ask, or we will end the session. Thank you. Thank you.
Madam, hello.
Yes, yes.
Adiabatic lapse rate always represented is positive, right?
Um,
Or negative?
the negative sign, it like
Yeah,
as we go
yes,
up in,
negative sign.
uh,
But it will be always, it is a positive quantity, no?
the negative sign basically represents that as we go up in the atmosphere, there will be a decrease in temperature actually.
Decreases. Yes,
Yeah,
yes.
so it basically represents the decrease actually. Suppose in the
Decrease.
surface we have 25 degrees Celsius and we go up
Right.
to 24 degrees Celsius, there will be a decrease by 9, like, yeah, 9 degrees Celsius
9.8.
per kilometer. Yeah, that's what it is telling.
Okay.
So that's what the negative sign denotes.
Okay.
Thank you.
Thank you. Thank you, madam.